So we are continuing on our exploration of stoichiometry, and now we're going to involve chemical reactions and with stoichiometry. So a liquid propane tank at a home barbecue has 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So if you look at this chemical reaction here, we have, this is propane. Propane reacts with oxygen to make carbon dioxide and water. And we can use these in stoichiometric ratios to calculate the heat of the reaction. So associated. And so let's see here, 13.2, so 13.2 kilograms of propane. We'll do P for propane. And 1,000 grams per kilogram propane. And then propane C3H8, 3 times 12 plus 8. 3 times 12 is 36 plus 8, that's 44. 44 grams propane per mole propane. And now there is a 1 to 2,044 kilojoules of energy. So depends on which direction. If you want to say, I'll just do it without a direction right now. 2044 kilojoules per mole propane. Oh wait, I got this one backwards. Sorry. Mole propane, 44 grams propane. Oh no, I should use C38H, H8. Okay, so the kilograms propane cancel, the grams propane cancel, the moles propane cancel, and we're left with that. So let's see here, it's just, so 13.2 times 1,000 divided by 44 times 2044, and I'm getting 613, 200, 613, 200 kilojoules. How many sig figs we've got? We've got 3 equals 6.13 times 10 to the 5th, right? Yeah, 10 to the 5th kilojoules. So that's a lot of heat, a lot of energy. Yeah, so that's how you can do, is do the dimensional analysis and using the equation there. And the other thing is, with these reactions, now we have ratios. This one's easy because it's 1 to 1, but if you were to look at oxygen, for instance, it would be a 5 moles oxygen to 2044 kilojoules. And then depends on the direction, if where the heat is going in the system. So it's similar to the previous skills you've had. So let's look a little bit more. So magnesium metal reacts with hydrochloric acid by this equation. Determine the enthalpy change for the reaction of 0.15 grams, 158 grams of magnesium metal to make 100 milliliters of solution. HCl is sufficiently concentrated, so it means magnesium is a limiting reagent. HCl is sufficiently concentrated, the magnesium completely reacts. Temperature of the solution raises from 25.6 to 32.8, and then what is the delta H? Use 1 in density solution and the heat capacity for water. Okay, so the temperature is going up, so that means that our delta H, I always think of the energy, delta H is negative. So delta H is negative for this reaction. And let's look at some things here. So the heat flow, so the heat is equal to mCs delta T. And it's the solution of the water, so 100 grams of water times specific heat, 4.18 joules per gram degree Celsius, times delta T, 32, it's an ugly 3, 32.8 minus 25.6 degrees Celsius. Okay, so I can put that in my calculator. Okay. So do the 32.8 first, minus 25.6. That's 7.2 times 100 times 4.18. And we get 3009.6 equals 3009.6 joules. Again, so now we have 3,000, too many zeros, 9.6 joules per 0.158 grams magnesium, and then it's I think it's 24.3 grams magnesium mole. I don't remember. I think it's 24.3 magnesium. Yep, I was right. 24.3. Okay. You do this enough, you too will be a walking periodic table. Okay. Then, so doing that, we have to multiply by 24.3 and divide by 0.158. And we get that's 4. 462.868.8. Okay, so let's see, what is this looking for? Determine the enthalpy change for this reaction. Okay, so, and this is joules. Joules per mole magnesium. And now let's start thinking about the direction. We mentioned that energy is leaving the system, so it's the negative direction leaving the system, and it's typically written in kilojoules per mole. And how many sig figs do we have? We have 3 for the temperature, so this is going to be minus 463, well, let's say, because it goes to here, 0 kilojoules, which would, by sig figs would be 4.63 times 10 to the third kilojoules per mole. Oh, negative sign. So there we go. Direction and sig figs for that one. Okay. So let's talk about relationships involving delta H here. I'll zoom in here. Might be easier to see it this way. If a chemical equation is multiplied by some factor, delta H is also multiplied by the same factor. Makes sense. If I can drive 35 miles on 1 gallon of gasoline, I should be able to drive 70 miles on 2 gallons of gasoline, assuming the same conditions, right? So I get this much energy from 1 donut, I get twice as much energy from 2 donuts. And I get half of that from the half of the donut. So if a chemical equation is reversed, delta H changes sign. So the amount of energy I get by burning glucose is the same amount of energy that plants have to put into glucose in photosynthesis. So going one way, opposites go the other. And if a chemical equation can be expressed by the sum of the series steps, delta H for the overall reaction is the sum of the heats of reaction for each step. Okay, so this is known as Hess's law. And you're like, why do I care? Why is this important to me? There's an old saying that says that a day in the library will save you a month in the laboratory. Of course, that's an old saying, so now it's probably a month in the library with maybe some internet access, or maybe a really nice internet access connection at home with access to journals and thermodynamic data will save you a trip to the school for a month to do it yourself. So many times, I mean, of course, if someone's already solved your problem, you can find it on the internet. And as it is right now, only humans can do that. We don't have artificial intelligence that's smart enough. So we have artificial intelligence that can like fly airplanes right now and do some diagnostic things, but an AI could not do something like this yet. So, well, we probably could do it to do Hess's law, but as far as searching for thermodynamic data and then solving a problem, my point is also, and I'm trying to fumble through my words, is that when you get a problem in real life that you have to solve something, it's not going to be all presented pretty like it is here in your training in academia. You're going to have to hunt for it. You have to look for things, and you probably won't find it. Like, this is when you can't find things. So that's when you have to take data and you have to tweak it. And then that's where Hess's law comes into play. This is where that would be useful if you find incomplete information, but there's enough there that you can figure something out. So this is one actually pretty easy to figure out. What's the delta H for this reaction? The heat of formation of propane. So 3 carbons plus 4 hydrogens makes C3H propane. So I don't know how to do this, so we can't. This is actually also something that would be really hard to do in a laboratory. You could do it. You could take some carbon and some hydrogen and kind of tweak it a little bit, see if it'll react, and then measure the temperature change. But that would be really difficult. I don't know that, but you know what I like to do is I like to burn things. So I'm gonna burn propane. I'm gonna burn carbon. I'm gonna burn hydrogen, and I'm gonna laugh a little. I gotta work on my evil laugh. So after I've burned everything, like, now I know what to do. Or I can look it up in the library. Okay, but when I do these, so first of all, I take these numbers and I assign them just values. And then I put all the reactants on the left and all the products on the right. So the first equation here, what I do is I'm going to flip it because I know that the C3H8 is on the right. So I'm going to flip it. 3CO2 plus 4H2O yields propane plus 5 oxygen, 5 water. And now to keep track, we're minus H1, and then carbons on the left, so we're going to keep this C plus O2 makes CO2, and this is H2. And then 2H2 plus O2 makes 2H2O. And this is H3. Okay. So now we need to add these together so they equal this. And we are going to have to figure out what variables to multiply things as. You can look at it one of two ways. One of the ways is we want to get the proper reactants, so we need 3 carbons. So we need to multiply this one by 3. And we need 4 hydrogens. So we're going to multiply this one by 2. That's one way to look at it. The other thing is you can look at it in terms of, I want to get rid of the intermediates, so the things that don't matter. So we've got 4 waters here, and so I can multiply this bottom one by 2 to get rid of those 4 waters. And I have 3 CO2s here, and so I want to get rid of the 3 CO2s from there. So those are the strategies, whichever one works better for you. Okay, so let's go through, and if you've noticed, the 4 waters cancel. The 3 CO2s cancel. And then we have 5 oxygens here, and 3 plus 2, that makes 5 oxygens, so the 5 oxygens cancel. And it's just like canceling things on a math equation. And what we are left with is 3C plus 4H2 yields C3H8. and then this is 3H2 plus 2H3 minus H1 in terms of the heat, and then you just go through and put those numbers in the calculator. So let's see here, 3 times the quantity negative 483.6 plus 2, so that's 3 times, oh wait, I got H2, wait a second, I got it backwards. Sorry, it's 393.5, 393.5 is H2, plus 2 times 483.6. That's a negative. I should put a negative. Don't forget the negative as I'm talking to myself. And then plus, that's just 1H1, 2043. And we were left with the negative 104.7. And this is equals negative 104.7, and how many sig figs? Yeah, that's fine. So yeah, kilojoules. So, and there we go. That is how you do that one. I think these can be kind of fun when it's all laid out for you. Fun when you're in the library looking for the stuff, it's frustrating. But doing this on your own in these books examples, they're kind of fun. All right, let's do the next one. Does the delta H reaction for this N2O plus NO2 mix 3NO. Okay, so pause this and try this on your own, and I will work my way through it. So go ahead and pause your stuff right now, and I will work on this now. So we want N2O plus NO2 making 3NO. And let's see here. So we're gonna flip the other one. 2NO2 going to 2NO plus O2. And this is minus H1. And the other one, NO is the other way. NO, 2NO. Oh wait, we want to leave that one the same. We want to keep that one as is. N2 plus O2 makes 2NO. And then this is fine, 2N2O yields 2N2 plus O2. All right, so, and we did not flip this one. This is H2, and we did not flip this one. This is H3. Okay, so now we've got to arrange them so we have that. So we're going to add these. So I think we multiply this one times 2 to get that. And by adding them together, we will then, I'm thinking this in terms of getting rid of the intermediates. So we get rid of these two NOs, and then this gets two O2s here, and then we can cancel these O2s, and we are left with 2NO2 plus 2N2O yields, so 2 plus 4 is 6NO, and this is minus H1 plus 2H2 plus H3. Then we divide this by 2, and you get NO2 plus N2O yields 3NO, and then it's just that value divided by 2. And then put it in and solve in your calculator. I guess you want to know the value, don't you? All right. So positive 113.1. No, and choose positive. Plus 2 times 182.6. And then, oh, times 2. Oh, sorry, there, 2, 2. And then H3 minus 163.2. And that divided by 2, we get 156. 157. So, looking at that, the answer is C. Okay. And that is it for this section. Next video coming shortly.